We're going to do one more example in section 11.1 on completing the square. Look at example 10 with me. This example looks a little bit different than the last couple that we've seen. What do you think? You notice that there's a number in front. There's a leading coefficient here other than 1. We haven't seen any completing the squares like this yet. And if you remember the steps for completing the square, the first thing we want to do is we want that number in front to be a 1. So what we have to do is make sure that we get rid of that 2. It's right next to the x, and so in order to make it a 1, we need to make sure that we divide by 2. But that means we have to make sure that we divide every single thing by 2 to keep the equation balanced. When I do that, I end up getting x squared, which is perfect, minus 5 halves x minus 3 halves equals 0. Now let's get the variables to one side and the number that doesn't have a variable to the other side. So I'm going to take that negative or minus 3 halves and I'm going to add it to the other side. So now I have the purple equation, x squared minus 5 halves x equal to 3 halves. Let's go ahead and finish completing the square. Let's figure out what number we need to add to both sides of the equation so that the left side turns into a perfect square factorable polynomial. Remember, we take the number in front of x, that's the negative 5 halves, we divide it by 2, or in this case, multiply by 1 half, which ends up giving us negative 5 fourths, and then we want to make sure that we square it, and that's the number we're going to add to both sides. We take the number in front of x, we divide it by 2, or multiply by the reciprocal, square that number, and that's the number we're going to add to both sides. So I have a negative 5 halves times 1 half, which is negative 5 fourths. I'm going to square it, which means I have positive 25 over 16. That's the number we're going to add to both sides. So when I go to factor the left side, what numbers multiply to 25 over 16 that when I add them together I get negative 5 halves? Ooh, that one's kind of hard. But do you remember the trick we talked about before? When I factor, it's always the number that I get when I divide that coefficient by 2. So negative 5 fourths should be the number that multiplies to positive 25 over 16, that when I add a negative 5 fourths and a negative 5 fourths, I end up getting negative 5 halves. Try it. Add them together, reduce, and make sure you get the negative 5 halves. You should, right? All right. Now what's going on the right side? It looks like I have a 3 halves plus a 25 over 16. I'm adding fractions. And now when I'm adding fractions, remember I need a common denominator. So let's make both of those into a denominator of 16. Let's multiply the 3 halves, numerator and denominator, by what, 8? And I ended up getting 24 over 16 plus 25 over 16. So I can really say on that right side that I have a 49 over 16. My left side is that perfect square. Now that I have that, I can finish solving by square rooting both sides. The square root cancel each other out. Remember, don't forget your plus or minus. And if you notice, the square root of 49 is 7, and the square root of 16 is 4. They happen to be also even roots. Perfect. So now we have no more square root. We just have regular fractions, regular numbers that we can continue working with. Let's go ahead and finish solving by adding 5 fourths to both sides. And they already have a common denominator, so that's nice. I end up getting x equals 5 fourths plus or minus 7 fourths. Now, please don't leave your answer like that. You wouldn't leave your answer x equals 1 plus 2, would you? No, you'd really say x equals 3 because you'd add those two numbers together. Well, same thing here. They're not radicals, so I have like terms that I should be able to combine and make my answers look a little bit nicer. I have two different answers. I have one statement that says x equals 5 fourths plus 7 fourths, and I have another one that says 5 fourths minus 7 fourths. Let's finish adding those fractions together. 5 fourths plus 7 fourths is really 12 fourths. 5 fourths minus 7 fourths is really negative 2 fourths. And then I can continue simplifying and really get two nice whole answers of x equals 3 and x equals negative 1 half. I don't have radicals in my answers like before because I ended up with roots that were even roots, unlike the ones that we did in the past. So I end up getting x equals 3 and x equals negative 1 half. No more radical. Now, because I didn't get a radical, what do you think that means about my original problem? Did anybody notice at the beginning what I could have done instead of this whole craziness with all these fractions? Ah, you could have factored, right? That one you actually could have factored using whatever technique you've learned. We've talked about bottoms up in the past, or split the middle term. You could have actually factored that one using bottoms up. Try it. It works, and you should still get x equals 3 and x equals -1/2 without doing all of this work. But you notice both techniques work. If factoring works, use it. If factoring doesn't work, though, then you have to make sure that you understand that there's another method, completing the square, that will also help you solve any quadratic.